All right, so this is our last lecture on truth tables. We'll talk a little bit about different kinds of sentences, our propositions, contradictions, tautologies, and contingent propositions, which we can use truth tables to identify. And then we'll show how to use truth tables to decide whether an argument is valid or invalid. All right, so complete truth tables for sentences work just like complete truth tables for the operators. A complete truth table for a proposition, I often use the word proposition and sentence interchangeably, you'll have noticed. So a complete truth table for a proposition provides every possible interpretation for that proposition. All right, so a tautology is a proposition that is true not once but always. It's true under every possible interpretation. We sometimes call these necessary truths. They are necessarily true. So if you look at a proposition like if P, then if R, then P, might not be obvious that this is necessarily true, but the truth table shows that it is. All right, so this is a truth table for an entire proposition that is different than the simple compound ones like P and R, etc. But it works the same way. So fortunately, we've only got two letters here, P and R. So we lay out the possible combinations, of which there are four because there's two letters, and then we assign all the corresponding values to P, R, and P, and then we just go ahead and evaluate. So we evaluated under the arrow TTT, FTT, TFF, and FFT, and this allows us to evaluate the main connective, the second arrow here, and we see that T, 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 F, F, remember, gives you a T with the arrow, and FT also gives you a T. So this shows that this is a necessary truth, true under all interpretations, and that's what a tautology is. Now, a contradiction is the opposite of a tautology. A contradiction is a proposition that is false under every possible interpretation. And we sometimes call these necessary falsehoods, and the book calls them truth functionally inconsistent. Now, one way we can make a contradiction very easily is just to take a known tautology and negate it, which is what we've done here. We just proved that if P, then if R, then P is a tautology, so by negating it, we get a contradiction. So false, 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 because we're saying not true, not true, not true, not true. So that's what a contradiction looks like. It will have false under the main connector, main operator, in every single case. Okay, a contingent proposition. Most propositions that we ever assert are contingent, and that means that contingent means it depends, right? So when we say that a proposition is contingent, we mean that it's true sometimes and false sometimes. And in logic, when we say sometimes, what we mean is at least once. So take a proposition like this: P and if R, then P, or we've stuck the conjunction in for the conditional. What we see, if we evaluate it, you're certainly in a position to do that yourself, is that under the main connective, which is now an and, we have some T's and some F's. And as long as there's at least one T and as long as there is at least one F, we'll say that truth value depends on the other assignments. In other words, is contingent. All right, so what we do is we just create a longer truth table, give it as much length as you need here, and put each proposition separated by a column we don't write in. Give each proposition its own little space. So we've got P or Q, not P, and we've got Q. And this little turnstile here is what we use to indicate that the conclusion follows from the proposition. So we'll say P or Q, not P, yields, entails, or implies that Q. And in this case, we aren't going to write anything under this column. Now I've simplified this a little with that, so I haven't gone and written all of the values in for P and Q here, so we can just see what this truth table shows. What this truth table shows is that there is no assignment of values to the individual truth values to the individual propositions that will give us true premises and a false conclusion. So here we have, with P or Q both being true, we have true, right? True, false, true, true, and false, false, false. So this proposition is true, this proposition is false. Okay, this proposition is true, this proposition is false, this proposition is true, and this proposition is true, but then the conclusion turns out to be true, not false. And here again, we have false and true. So because what this truth table shows is that because there is no assignment, no possible assignment of truth values to the premises such that the premises are true and the conclusion is false, this has to be a valid argument. Now, we can also show that an argument is invalid in the same way. Here's an argument: if P then Q, Q therefore P, which we've put up in exactly the same way, and interpreted, we get one line, and all we need is one. There could be more, but we get at least one line where the premises are true and the conclusion is false. And as long as there is at least one line in which the premises are true and the conclusion is false, then we have an invalid argument. Now, there's an interesting connection between a valid argument and a tautology, which is worth knowing about. So it turns out that any argument at all can actually be converted into a sentence in the following way. So look at this argument, the disjunctive syllogism, P or Q, not P, therefore Q. Well, you can actually read this argument as saying, if P or Q and not P, then Q, right? P or Q, not P implies Q. Or you could say, if you have P and Q and not P, then you get Q. That says the same thing. So you can take this argument here and convert it into a sentence. If P or Q and not P, then Q. Now what happens if you take that sentence and put it into a truth table? So you've got if P or Q and not P, then Q. If you work this truth table out, what you find is that all of the values under the main connective, which is the conditional, are true. True, 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 and true. And for practice, you should go ahead and make sure that's all correct. So what it turns out that if you take an argument and you convert it into a sentence, and if the argument is valid, then the corresponding sentence is going to be a tautology. So for this reason, we actually sometimes call tautologies valid sentences. We probably won't say that very often in this class. It's a little bit confusing. Generally, we like to just say that arguments are valid or invalid, but it's actually a quite common terminology. Look at this example. P, not P, therefore Q. Now, if you just looked at that intuitively, how would you assess it? Would you say that that's a valid argument or not a valid argument? I think for most people, intuitively, it's not a valid argument because you look at it and you see that Q is just coming out of nowhere, right? Where the heck is that coming from? How could you ever get Q out of P and not P? It doesn't really seem possible, and so it seems like there is no way the premises could imply the conclusion. It actually turns out that it is a valid argument, and we can show that with the truth table, right? So why is this a valid argument? Well, it's a valid argument. There's only one reason it's a valid argument, because there's no assignment of truth values to the premises where the premises are true and the conclusion is false. True, false, true, true, false, 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 true, true, false, true, true. What's interesting is the reason there's no assignment of truth values to the premises where the premises are true and the conclusion false is because there's no assignment at all in which the premises are both true, right? All of these are true, false, or false, true. None of them are true, true. And the reason for this is that P and not P is a contradiction, right? So there's no way to ever create a situation where the premises are true and the conclusion is false, specifically because there's no way to create a situation where the premises are both true in the first place. So that's kind of a strange degenerative case of validity, but it shows us two things. First, the idea of validity isn't completely intuitive. And so we'll sometimes wrongly assess the validity of even very simple arguments if we don't check them with a mechanical procedure. And second, the reason an argument like this one is valid is that it contains a contradiction. And you probably know intuitively that contradictions are not good things. We're generally critical of people who contradict themselves because it doesn't make any sense to assert something and deny it at the same time. So in logic, what we can say is the reason for this, the reason a contradiction is bad is because from a contradiction, absolutely anything follows, right? Q is just pulled out of nowhere, and you could prove anything at all if your set of premises is contradictory, and that is a bad thing. I mean, if you're able to prove anything at all on the basis of what you believe, there's something fundamentally wrong with your set of beliefs because not everything is true. Okay, so we noted that truth tables with n sentence letters have 2 to the n rows, and that means that a truth table, say, with 5 sentence letters will have 32 rows. 2 to the 5th is 32. And that really makes truth tables impractical for human beings. It's okay for machines because this is what they're built to do. They can assess truth tables in the blink of an eye. But it's a very tedious thing for human beings to involve themselves in. And that's why we go and develop other proof methods in propositional logic. But it's a rite of passage, really, to do at least one truth table with more than 4 rows. So let's do a truth table for the following formula. All right, so this one has 8 rows. 2 to the 3 is 8. And you'll see that over here we have to make sure we're getting all of the possible combinations, we have to make sure we distribute the truth values in a way that generates that. So here we have 4 T's in a row followed by 4 F's. Then it's TTFF, TTFF, and then alternating T's and F's, and that generates all of the possible combinations. So this is just, a little more tedious. It takes longer, but there's nothing especially different about it. You can see that the and here, this ampersand is the main connective, right? Should be fairly obvious to you now. And so some of the work is just the mindless activity of putting all of the corresponding truth values under the right sentence letters. So I've given F to not R to make that step quicker. And then actually, you can, if you're really just trying to get the fill out all of the values under the main connective, you don't actually have to do the whole truth table. For example, if you know this is an and, you know that the main connective is an and, so you know that in order for it to be true, then the whole then both conjuncts have to be true, right? So TF gives you F. And so you automatically know that this is going to be an F as well. Of course, you can go ahead and fill this in pretty quickly. Q if and only if R, T if and only if T is T, and T if and only if T is T. So that's T, and sure enough, T and F is still F, right? But you knew that already. So all you have to do is just go through all of those quite quickly, and you'd be done in a few minutes. When you're done, it's going to look like that. This is turns out to be F's, all F's under the conjunction, and so we've got a, what do you call this? This is called a contradiction. Whoops. Okay, or a necessary falsehood. All right. Now, one last thing we'll talk about is the way to use truth tables to quickly assess an argument as being valid or invalid. And that is, and this is so that you don't actually have to do the whole truth table. So this is what we call working backwards, which is sometimes we call this reverse engineering. So the way you do this is you actually leave all the initial assignments of truth values to the sentence letters blank, and then you just assign true to the premises and false to the conclusion. And this is normally going to force a particular assignment of subformulas. So by working backwards, you can figure out, working backwards on the assumption that the premises are true and the conclusion is false, you can figure out whether it's possible to fill things out, fill out the values so that you get that. And if you can't get it, then it's impossible for the premises to be true and the conclusion false, which means it's valid if you can, and you can do it with every single one of the assignments of true premises and false conclusion, then it's invalid. So let's see how that works. So we'll go ahead and use this method on an argument that has 4 sentence letters in it. So if we were going to do an entire truth table for this, it would require 16 lines. So this should end up saving us quite a bit of work. So what we're going to do is, so here's the argument, P or Q, if P then S, if Q then T, therefore S and T. So we distribute each of the premises across the top. And notice we don't fill anything in over here. But what we do is we assign true to all the premises. So true under the wedge, true under the arrow, true under this arrow, and then we assign false to the conclusion. Okay? Now what you can ask yourself is, well, how many ways can a conjunction be false, right? So the answer is that it can be false 3 ways, actually. So it can be false, false. It can be true, false. And it can be false, true, right? So those are all possible assignments of truth values to S and T that we might have to check. We might have to check all of these. But still, that's just 3. It's not 16. Okay? And the truth is that we could only get away with checking 1, right? Because we know that if it's impossible to, if it's ever possible to assign false to the conclusion and true to all the premises, so we get all these boxes filled out and it works, there's no resistance, there's no contradiction that results from doing that, then we've shown that it's invalid. You only need 1 line where the premises are true and the conclusion is false to show that it's invalid. But if it turned out that we couldn't make that assignment in the first line, then we'd have to keep going until we had checked all of these. But still, we only have to check 3, right? Because these are the only 3 ways that the conclusion turns out to be false. Okay, so got false, false here. We'll start with this one. And then you'll notice that when we put false under S and false under T, well, that makes us assign F here, and right, you got to assign F here and F here. And so we can just go ahead and write over here, S and T are both F. Okay, so far, no pressure. We're able to do that. So that's that. And then, so this is already all filled out. What else can we fill out? Well, we know that, look, this has to turn out to be true. And the only way that an arrow can be true, a conditional statement, can be true if the consequent is false is if the antecedent is true, right? So that's got to be false, which means that that's got to be false, which means that that's got to be false. So again, that works. We're fine. No problem so far. So we've got that. Now, the last thing there's only one other thing to do, and that's to do P, okay? So look at OR, all right? Now, if OR is going to be true, Q is already false, so this has to be true, right? So now we got to write true here. But here's the problem. We can't write true here. Right, we can't write true here because this has to be true, right? This has to be true. So that means this has to be false. So that has to be false. And that's the problem. That's a contradiction, right? You get forced by this way of doing things to assign both T and F to P, and that's not legitimate. So what have we learned from this? Well, what we've learned is that at least with this one line, it is impossible to assign true to the premises and false to the conclusion, which means that as far as this one line is concerned, this argument so far is valid. But the problem is, as we said earlier, there's three others that we would have to check, right? Validity can only be established by the whole truth table with the assignments of true to the premises and false to the conclusion. Invalidity can be established with just one line. So that means we've got to do another one. Okay? So which one should we do? Well, take your pick. Here, I'm just repeating what we just said. So you can't have both T and F, right? So this shows that with this particular way, in this first line, it's impossible to make the premises true and the conclusion false. Okay, so let's try again on the second line, and we can take our pick of truth values here. Let's go ahead and assign this time T and F, right? So that means S has to be T over here, right? And F has to be T, or T has to be F here. Stop that. And so S is T, and F, right? So far so good, and then so that's that. And then we can go ahead and same reasoning, right? Let's go ahead and look at Q. What does Q have to be now? Well, this has got to be true still. That's false. So, of course, this is still just false again. So false, false, and Q is false, like that. And so, again, once again, it all comes down to P. Okay, and so here we have, again, this is required to be true, right? This is false, so this has to be true. And consequently, this has to be true. And the question is, can it be true? Well, as a matter of fact, now it can be, right? Because if true, then true is true. So here we have actually succeeded in filling out a line where the premises are true and the conclusion is false. We've completely filled this out with no resistance, no contradiction. And so what that means, that sounds all positive, right? And when it's positive, we think of positive things like valid. But what this means, having accomplished this, means we have shown that it's invalid, right? This is invalid, right? Because an invalid argument is one in which it's possible to assign true to the premises and false to the conclusion. So that's a very easy thing to just get sort of momentarily confused about. All right? Okay, well, let's go ahead and look at a similar looking argument. The only difference actually is going to be that there's going to be a disjunction here. So P or Q, if P then S, if Q then T, therefore S or T. So again, we just assign true to the premises, false to the conclusion. And this one looks like it's got to go a little faster, right? Because there's only one way for a disjunction to be false. The only way that a disjunction can be false is if both disjuncts are false. So we're forced. There's no other line to consider. This is all or nothing, right? We're forced to assign false to S or T. False, false. That's the only assignment possible, right? So that means false here and false here, right? And then we can go ahead and ask about Q. Well, if this is going to be true, then Q is going to have to be false, just as before. And once again, it all comes down to P. Oops, Q is going to be false here. Okay, so if this is going to be true, then P is going to have to be true. But just as we saw in the first example, here, P has to be false, right? P has to be false because the only way that you can make a conditional statement with a false consequent true is by making the antecedent false. So this is no good. This is a inconsistent assignment of truth values. And what does this mean? Well, we're saying it's no good, it's bad. What this actually means is that the argument is good. This is valid because this is the only line we have to consider, because this is the only way that we can make this false. It's valid because it's impossible to assign true to what? The premises, and false to the conclusion. Okay, that's just the definition of validity. In logic, we're just always appealing to the definitions. Okay, and this is just working it out for you if you just happen to be looking at the slides instead. All right, so we'll just finish up with a few study questions here, and that's that. Again, make sure you pause this as soon as you get to one that you're working on, because I'm going to give the answer pretty quick.